Okay, good afternoon everyone. So this is our fifth week of live tutorial session, and today we'll be discussing some problem based on basis and dimension of a vector space. So let's start with the basic definition of basis and dimension. How is it defined? So first basis. So suppose V is a vector space. I will assume this V is a vector space over field K. Then a set of vectors in V is called said to form a basis of V. So a set of vectors vectors say Vi, I belongs to I, or write this one, I belongs to some index set I is called a basis of V if this set is the above set is linearly independent as well as that generates the vector space V is a generating set of V. That means each element of V you can write as a linear combination, finite linear combination of the vectors Vi, and linearly independent means that if you choose a linear combination of Vi that if that is 0, then the coefficient all of the scalar that you considered with Vi, that those must all be 0, right? So and they are linearly independent. Then you call this as a basis of V, right? And what is dimension? Dimension cardinality of a basis is called the dimension of that vector space. So it is well defined due to that H. So the remark is that as each basis has same cardinality, so the dimension is well defined. Also in the class you have seen that this basis is a minimal generating set for the vector space V, and it is a maximal linearly independent subset in the vector space V. So when you know that the dimension of a vector space, suppose the dimension is n, finite dimensional vector space, so dimension suppose n, then if you have n linearly independent vectors in the vector space, then that will be a basis of your vector space. Or similarly, if you have like n vectors which generate your vector space, whole vector space, then that will also be a generating like basis. So that's enough, I think, for the theory. So let's go to one problem first. So this is basically to show that this forms a basis of Kn. So suppose lambda 1, lambda 2, lambda n are pairwise distinct element in a field K, and you define vectors x1 to xn like this. x1 is just, so we know the dimension of this k power n over k is n, right? Because this 1 0 0 0, so delta I n for like n belongs to like I equal to 1 to n, that forms a basis. So first that k power n has dimension n over k as this set, so those are the right ends as ei by definition. This is delta ij 0 less equal to j less equal to, or sorry, 1 less equal to j less equal to n. This then you have at the, so ei basically at the ith position you have 1 and elsewhere you have 0, so this set has 1 less equal to I less equal to n is a basis of k power n, right? So this is basis, I know. Now to show this x1 to xn is also, these are n vectors, so to show these are also forms a basis, it is enough to check that this x1 to xn are linearly independent or generating set. So in this case I can only check the linearly independent C, because generating that will follow using this dimensionality. Okay, so enough to, so enough to check this x1 x2 dot dot xn is linearly independent. So suppose consider Ci, or let's say ai xi I equal to 1 to n, this equals 0. Okay, so each x1 x2 xn, they are vectors in k power n, right? And they have this this thing that 1 lambda 1 lambda. So from this I can also write like these are n tuples. So if I just write it in the form that a1, so let me write this x1 as column vector instead of row vector. So if I write them, then this is 1 lambda 1 square up to lambda 1 power n minus 1, and then this is a2 1 lambda 2 square lambda 2 power n minus 1 plus an 1 lambda n square lambda n power n minus 1, and this equal to this 0 means the vector 0 0 0 0, right? Everything this is happening in k power n. Okay, now to prove this ai, let me use that this xn is linear independent. To check this one, I'll use the induction on n. Okay, so what that means on induction on n, so we'll proceed by induction on n. So let me then erase this part. So base case of the induction is true, because so for n equal to 1, for n equal to 1, this there is only one vector x1, and that is defined to be just 1, right? Because that, and 1 generates your generates the vector space k over itself. So for n equal to 1 it is trivial. So for n equal to 1, x1 equal to just 1, is a basis of k power n, that is k over k, right? So suppose it is true for n minus 1. Suppose the claim, that means this x1 x2 xn minus 1, which is defined like, okay, so true for n minus 1, okay, that is so that is this. If I define x1 prime, that will be 1 lambda 1 lambda 2 up to lambda 1 to the power n minus 2. Okay, so let me in general define lambda I, xi prime. Xi prime is this 1 lambda I square all the way up to lambda I power n minus 2. Okay, so this belongs to kn minus 1 for 1 less equal to I less equal to n minus 1 is linearly independent is enough for us, and that will give the basis. Okay, so are linearly independent. And for this I equal to n, I can also define, because I have this lambda 1 lambda 2 lambda n. So for lambda n I just can define and also define xn prime equal to 1 lambda n power n minus 2 belongs to kn minus 1. Okay, now to show that like go back to this thing, the linear for n elements x1 x2 xn. So now suppose this one, then this relation is equivalent to, this relation I can equivalently write the first n minus 2 relation. That means this, if I go to 1 lambda 2 square up to lambda 1 to the power n minus 2, then I can write those by this definition, that is same as ai xi prime, right? This xi prime, because this is to n minus 2, so this I equal to, so this is I equal to 1 to n, this equal to 0, those vectors I have defined here. And also I can also together with the last equation, but that I can again combine, like ignoring the first a1 plus a2 plus an equal to 0, ignore that and take that to be just lambda 1 a1 lambda 1 square lambda 1 into lambda 1 square lambda 1 up to the n minus 1. So and that thing is same as, just I can take lambda 1 common, so that is a1 lambda 1 into 1 lambda 1 square up to lambda 1 to the power n minus 2. So that thing again same as ai lambda I. If I take lambda I common, then that is same as xi prime, right? Again the same vector, so I equal to 1 to n, and that is 0. Now if I combine these two, so I somehow want to use the induction hypothesis here, that this is linearly independent. So the extra vector here only is xn prime, right? So xn prime, if I just like eliminate that, then I'll get I can use the linear independence of xi prime. So suppose this is my equation number 1, this is equation number 2, say their vector equation. So multiply this first equation by lambda n and subtract it from like equation number 2. So this is same as combining like ai lambda n minus ai lambda I into xi prime equal to 0, I equal to 1 to n. So using multiplying 1 by lambda n and then subtracting the equation number 2. Okay, so using this one. But for the I equal to n, this is lambda n, a n lambda n minus a n lambda n, so that thing is 0. So this is same as I equal to 1 to n minus 1 ai into lambda n minus lambda I into xi prime. Now so this relation, so as we know, x1 x2 x1 prime x2 prime up to xn minus 1 prime, they are linearly independent. So this is a linear combination of those vectors which equals to 0. So I must have all the coefficient of those that linear combination, that is 0. That means ai times lambda n minus lambda I, this is 0 for all. So 1 less equal to I less equal to n minus 1. Right, now ai belongs to this ai, so this ai belongs to k, is a field. This lambda n minus lambda I, that is also belongs to my field k, and lambda 1 lambda 2 and lambda n all are pairwise distinct. So lambda n minus lambda I for any I belongs to 1 to n minus 1, that is non-zero, right? So both ai and these are non-zero. Like ai I don't know non-zero, but this is non-zero and their product is 0, as k is a field. So I have this inverse, so this implies ai equal to 0 or 1 less equal to I less equal to n minus 1. So as lambda n minus lambda I not equal to 0, and that belongs to a k. So it has inverse, I can multiply both sides by its inverse, I get ai equal to 0. Okay, and that here we are only using the fact that this lambda n's are distinct number element. Okay, and this is by induction, like induction state. So this shows that this all the way 1 to n minus 1 is 0. Now if I put here 1 to n minus 1 all ai is 0, so that remains only a n xn equal to 0. But a n xn, that this xn vector, this is clearly non-zero because the first coordinate is 1 itself. So that is 0 means a n is also 0. So combining with that, so thus a equal to 0 for 1 less equal to I less equal to n minus 1, and a n xn equal to 0, that is n equal to 0. So this means a equal to 0 for 1 less equal to I less equal to n. Hence this x1 x2 xn is linearly independent. So this is fine, right? Okay, so let's go to the next problem then. So it is like similar problem, but little bit easier one. So again you have to show that this is enough to show that this is linearly independent, and then it will form a basis of k power n. So again just exactly, so you can consider this to show that these are linearly independent. You consider this vi yi, that is 0 for I equal to 1 to n, or bi belongs to k. I need to show that this b1 to bn all are 0. Now this is 0. If I just expand using the given definition of this yi, I'll see that this is same as bi into lambda, so lambda j power I minus 1, I equal to 1 to n. This is 0 for j equal to 1 to up to n. Okay, because this b1 y1, that coefficient is always b1, then b2 y2 is, that means always it is some lambda j b2, and similarly up to yn this is bn lambda j power n minus 1, right? So this says that this that is same equivalent to this one, right? So now this is saying that if you consider this polynomial fx bi x power I minus 1 for I equal to 1 to n, so this is a n minus 1 at max n minus 1 degree polynomial over k. So this belongs to k x n. So this kx n denotes the set of all polynomials on the degree less than n. So this is degree less than n, so clearly this belongs to this. So has n distinct root, right? N distinct roots, lambda 1, lambda 2 up to lambda n, because this lambda 1, lambda 2, lambda n's are distinct and they all satisfies this f of lambda j, any j for any j equal to 1 to n, this f lambda j that is equals to 0 by this, right? So this has this many roots, so it has so fx is a degree at most n, but it has n distinct roots. So that can happen only if and only if using fundamental theorem of algebra, that this implies all the coefficient bi must be 0. So because any degree n polynomial can have at most n roots in the field, right? So I have this bi equal to 0 for 1 less equal to I less equal to n. So by fundamental theorem of algebra. So this implies your this y1 up to yn is linearly independent. Fine. This is just easy consequence of this. Okay, so let's go to the next problem then. So here you are given V is a finite dimensional vector space, and in particular this dimension is n, and U is a subspace of that vector space P, and it has dimension m, so m less equal to n, and u1, u2, um is a basis of U, and u1 u2 um up to un is extended basis of v, right? Then if you take x any element, so if you take any element x in this vector space that is written as the linear combination of this basis vector u1 through un, then that belongs to your subspace u if and only if the coordinates this with respect to the basis u1 through un all are 0. Okay, so remember this um plus 1 star x, that means it captures the m plus, like the coordinate of m plus 1 uh, coordinate of um plus 1 in the this form of x. If you expand this x in the form of this u1 through um, then it just captures the bm plus 1 vectors. So in particular it is taking at the um plus 1 vector 1 and everything else vector it is 0. Okay, so this is again, right? Suppose take this forward part. Suppose x equal to this ai ui I equal to 1 to n. This belongs to, this is obviously belongs to v, but let's belongs to u. Okay, so then I need to show that this bm okay, so this is till m, sorry, so a1 to m, this is till, and then you have I equal to m plus 1 to n, this is bi ui. Okay, this is belongs to u. Now you need to show that these all this bm plus 1 bm plus 2 all the up to bn they are 0. Okay, so as this belongs to u and u1 to um, this is forms a basis of u, as u1 up to um is a basis of u. So I can write x equal to some ci ui, right? I equal to 1 to m, but I also know x has this expansion, so then this summation ci ui I equal to 1 to m, this is equals to summation I equal to 1 to m ai ui plus b I ui I equal to m plus 1 to n. Okay, now just take this thing in one side, so this is I equal to 1 to m ai minus ci ui plus I equal to m plus 1 to n bi ui, this is equal to 0. Now this u1 through un, this forms a basis of v, so in particular they are linearly independent, so I must have this all the coefficient is equal to 0. That means ai equal to ci for 1 less equal to I less equal to m, and bi equal to 0 for m plus 1 less equal to I less equal to n. So by linearly independence. Then see of this u1 up to u1. Okay, so that completes this direction, that this all this bi are 0. So and conversely it is like trivial converse, because if I have this b1 bm plus 1 up to bn all are 0, then this is linear combination of vectors of u1 through um, and u1 through um forms a basis of u. So conversely So bi equal to 0 for 1 m plus 1 less equal to I less equal to n implies x equal to summation ai ui from 1 to m, and this clearly belongs to u. So this is like very easy thing. Okay, so okay, so then let's go to the next question. So in this question you have suppose the dimension of the vector space V is n, and if you have the hyperplanes h1 up to hr in V, then you need to show the dimension of the intersection of h1 up to hr over k is at least n minus r. Okay, so then let's do that. So recall that hyperplanes in V means the codimension of the each of these h1 up to hr is 1. That means their dimension is n minus 1 because V has dimension n. So h1 up to hr are hyperplanes in V. So this implies the dimension of hi over k, this is equal to dimension of V minus 1, that means n minus 1 for I equal to 1 to up to r. Now we need to show that this equal to getter equal to n minus r. So let us like proceed by induction on r. So proceed by induction on r. Okay, so for r equal to 1, for r equal to 1 you have only hr, so sorry h1, so dimension of k h1, that is exactly n minus 1, and here r equal to 1, which is getter equal to n minus r, that means n minus 1. So true for r equal to 1. Statement is true for r equal to 1. Suppose it is true for like r minus 1, that means r minus 1, that means that dimension of h1 intersection up to h r minus 1, this is getter equal to n minus r minus 1. Okay, so I need to show the dimension of h1 intersection hr is getter equal to n minus r. So now recall this thing that okay, call this theorem that dimension of like VW are two vector space. Suppose if U W are two vector subspaces of a vector space, V, then okay, over K say then dimension of u plus w, this sum is happening inside V. This is exactly equal to dimension of u over k plus dimension of w over k minus dimension of u intersection w over k. As everything is happening, this u plus w is a subspace of V, so I can always write this as this dimension is less equal to dimension of k over V, right? As u plus w is a subspace of V. So this implies I can write that dimension of u intersection w, so dimension of u intersection w, this is this is greater equal to dimension of u plus dimension of w minus dimension of V, right? So everything these are like infinite B is a finite dimensional vector space, supposing. Okay, so everything these things make sense. Now in our case we will apply this thing for the subspace H1 intersection H2 intersection HR minus 1 and HR. Then on one side we will get the required H1 intersection H2 intersection HR, and on the other side we have this thing and HR and V. All the things are like known to us. Okay, so now applying the theorem for u equal to h1 intersection up to hr minus 1 and w equal to hr, we get dimension of h1 intersection hr minus 1 intersection hr over k is greater equal to dimension of h1 intersection hr minus 1 plus dimension of hr, everything this is over k, minus dimension over of v. Okay, so in our case dimension of v is n given, so if I put here like dimension of h1 intersection h2 intersection hr minus 1, that is greater equal to n minus r minus 1, so this is greater equal to n minus r minus 1, and then this dimension of hr is exactly n minus 1, so and dimension of v is again n, right? So this is equal to, this is exactly equals to n minus r, right? So this completes the completes the induction process, hence this is the Now for the B part, again you need to find such, like if you are given a subspace of codimension R, then these questions like claim that you need to show that there exist R hyperplanes such that you can write U as intersection of those R hyperplanes. from previous part we know that this, if you take R hyperplanes and take their intersection, their dimension is at least n minus r. And also in this case also your given U has exactly dimension equal to n minus r, because codimension r. So you somehow need to guarantee that this dimension is exactly n minus r and it contains also U. So that thing is again like extension theorem kind of we can use. Okay, so let's put that. So given dimension of U, this is dimension of V minus R, that means n minus R. So take basis, we can take basis, so take a basis U1 up to Un minus R of U in V over the field K. So then extend this, I can extend this basis to a basis of V. This basis to a basis of V. Basis that will contain L element, so Un minus R, Un minus R plus 1, the other to Un, basis of V over K. So now we can consider like this define, like I want to get like this H1 intersection H2 intersection HR, that should be precisely my U, right? But that means in particular that each of these H1 contains U. So whatever HI I will define, that must contains this U1 through Un minus R, right? And their dimension is exactly n minus 1, so I should delete exactly one element from the remaining this n minus r, like n minus Un minus R plus 1 through Un. So it is natural to define this Hi, that will I will define this U1 up to Un minus R. So once I take this, so this is like span of, I should write span of this, not exactly span. So that means this is subspace generated by these vectors Un minus R and up to Un minus R plus 1 and so n minus 1, or I should define like n minus I up to Un hat. Okay, so hat means this, you delete this, or okay, so this might n minus R minus I. Okay, n minus R minus I. So H1 is, if you take I equal to 1, this is deleting the n minus R plus 1, this vector. So you take all the vector except Un minus R plus 1. U2 is n minus R plus 2 and so on. Hn is, you are like not taking the vectors Un, right? So so 1 less equal to I less equal to R. So then Hi is a hyperplane, in in V, because this dimension exactly defined this all the u1 through un, they are linearly independent, and I'm deleting exactly one vectors from them. So it is a subset of linearly independent set, so that is again linearly independent, so dimension will be exactly equal to n minus 1, and so it is a hyperplane in V. So now my claim is that this hi intersection h1 intersection h2 intersection hr, that is precisely u. Okay, so first of all, this note that this u is contained in hi, right, for all I equal to 1 to r. So this implies that u is contained in like h1 intersection h2 intersection hr, and also I know the dimension of u is, so this implies dimension of okay, already I know that this dimension of, by previous part, dimension of h1 intersection h2 intersection hr over k is greater equal to n minus r. Here also we are getting exactly u also has dimension n minus r, but note that this u1 into un minus r, these all belongs to here, but no one of these other vector un minus r plus 1 and like un minus r plus 1 through un, none of those vectors belongs here, because at least one hi does not contain that vector, right? So dimension of k h1 intersection h2 and so mostly like, and also this is containing u. You don't need to go to dimension. This implies you have hr exactly equal to u. This intersection like belongs to hr, because if I take any element, so let me put it here, like if x belongs to h1 intersection hr, then I can write it like x in the linear combination of vectors of this form, but note that each u or that thing is missing here. So this, like using the previous theorem that we proved here, once you say that this belongs to hr, so I can write this as ai ui I equal to 1 to n minus r plus, so this implies x equal to this thing, and sum bi ui I equal to n minus r plus 1 to n minus r. Yes, so this thing belongs to hi, or let's say hk for 1 less equal to k less equal to r. So this implies that if I consider this is belongs to h1 and that is belongs to h2, so that will imply that your both the hn minus so the coordinate of this un minus r plus 1 and un minus r plus 2, those coordinates are 0. So if I do for all those, so I must have bi equal to 0 or n minus r plus 1 less equal to I less equal to n. So using previous exercise, right? So so that gives me that x equal to sum of ai ui I equal to 1 to n minus r, and that is belongs to u. So that's why this inclusion is there, and hence you have this required thing. Okay, so this is the related to like any subspace of a finite dimensional space. You can write that as a intersection of hyperplanes. For example, like in R3, if you take a straight line that is a co-dimension 2 subspace, you can write that is a intersection of two planes containing that, right? Similarly, in general, that also happens here. That's what this problem is about. Okay, hope this is clear. Now let's go to the next one. Okay, so here this is like again related to finite fields. Okay, so and the characteristic of a field. Okay, so so here you have a finite field K with Q elements, and then it is claiming here that there exists a smallest positive natural number P such that 1 dot P dot 1K, that is 0. That means if you add the multiplicative identity in K, namely 1K, P times, then that will give you 0 element. Okay, and moreover this P is prime, and this P is called the characteristic of P, and that is denoted by like char K, characteristic char K. Okay, so how do you show that this one? So this is again like basic group theory. Like here you have K has Q elements, so you can consider like this set, this let's say m dot 1K such that m belongs to Z. This is well defined because I can take for any positive integer for m equal to 0, this is simply 0. For any positive integer, that is just adding 1K that many times, and for negative one I am adding minus 1 that many times. Okay, so this is a this is clearly a subset of K, right? Because everything, this K is a field, so this is closed under addition. I am doing all the addition here. So this is a subset of K, and K is finite, right? And mod K is Q, finite. But this thing is like Z is infinite, this seems infinite, but that cannot be infinite, but this is a subset. So I must have, so there exist, so this implies there exist like elements, there exist let's say Mn belongs to Z such that, so these cannot be all distinct, right? Because if all these are distinct, then I would have get infinite thing, and infinite thing cannot be lie inside K. So this cannot be all these m into 1K, m plus 1 into 1K, that those cannot be all distinct. So I must have integer mn belongs to Z such that m into 1K is n into 1K. So that means m minus n, so obviously m and n distinct, so mn, let's say, so distinct such that this is the case, this is 0. So in particular I can say that there exist integers, say q, such that q into 1k equal to 0. So now we can consider this set. So obviously this q is non-zero. So consider all those q belongs to natural number set like star, so it is except the 0 thing. So 0 such that q dot 1k equal to 0. This is clearly non-emptied because by the above thing this is not, so this is not equal to 5, and it is a subset of the natural number set n star. So by OL ordering principle, well, there exists a least element in this set. So this set is suppose S. Principle S has least element. Least element say P. Hence we have the required claim like this thing. So hence there exists a smallest natural, like positive natural number I should say, smallest positive natural number P such that P dot 1k equal to 0. But moreover I need to show that this is prime. This is prime simply because this k is a field. How? So second part say, so if P is not prime, then I can write P as like, then P I can write as like P1 into P2, where P1 P2 both are like not equal to 1, right? So P1 greater than 1, P2 greater than 1. So then what I get? So on one hand you also have P dot 1k equal to 0. Then this P dot 1k equal to 0 implies P1 P2 dot 1k equal to 0. But P1 P2 dot 1k equal to 0 means P1 dot 1k into like P2 dot 1k. This is 0. This is simply using the distributive property. Like this means that you are adding 1k P1 into P2 times, but that is same as you first like add 1k P times and then multiply with 1k added P2 times, right? So this is simply by distributive property of plus and dot in the field. Okay, so by distributive property. Property of or property K. Okay, but this thing is non-zero, right? This thing is non-zero. This thing is also non-zero because this P1 P2 are less than P, and by our choice this P is the least element, least positive element, such that this p dot 1k equal to 0. So both this p1 dot 1k and p2 dot 1k both are non-zero, but their product is 0. That is a contradiction, which is a contradiction, because in a field there is no zero divisor, but here you get a zero divisor. Multiplying two non-zero elements, you get 0. Contradiction to contradiction for k to be a field. Hence p must be prime. Right? Okay, so there are some other question related to this thing. This thing is doable. You try this. I will write some of this thing in hint with the PDF. I'll attach that in description box. Please find that. And there are also some other question, we may discuss those questions next time. So this is enough for today, and we'll discuss some more problem related to basis dimension if possible in the next tutorial. Okay, so hope there is no question. Okay, so then I'll stop here. We'll meet next week.